Hmm. So we were discussing in our last video corresponding to this diagram. So after receiving the data at the destination, after so short interframe space, destination will share back the acknowledgement. So others will also come to know about this acknowledgement, and then they once again can start the phase of contention again. What this network allocation vector is, so while sharing this RTS, source will also share the time for which it wants to get into sort of a communication with destination. So sort of a time frame that destination will be busy for this much duration. That means source wants to hold the environment, wants to hold the resources, the channel resources for that much duration. That information would be there. So that information, while sending back the CTS, that information would be relayed to other uh, competitive nodes as well, which are competing for the resources, for the channel resources, so that they would come to know about the duration for which they have to wait. So that goes as a network allocation vector. So in the network allocation vector, it is nothing but a time duration. So during that time duration, always is that nodes will check their network allocation vector first. So once all these competing nodes receive the CTS, they will start their network allocation vector. So that is a sort of a timer. So then they keep sensing whether that network allocation vector is zero or not. Once it will become zero, that means then they can compete. They can contest for the channel resources. That's it. So here you can see that after this IFS, then the contention window, then RTS being shared with the destination. Then after sending the RTS, the sender node will start its timer because it would wait for that prescribed time for CTS to come. Once the CTS will arrive or not arrive, it will sense it, it will check it, whether the CTS received or the timer times out. Both the situation, if it is true that you have received the CTS, if you haven't received the CTS, means it is a sort of a failure. In that situation, you will increment your k equal to k plus b, and then you will check whether the k is less than limit. If it uh, overshoot the limits, then that means you have to simply abort the operation. Otherwise, you will wait for TB amount of time. This TB amount of time is also once again based on whatever the random number you will choose, and based on that random number, then either you will multiply it by the transmission time or the propagation delay. Based on that much amount of time you will wait. After waiting, you will once again sense and do the whole operation again. So here after sending it to, means after receiving CTS, you will wait once again for that SIFS time, and you will send the frame. So this is the transmission phase. After sending, obviously you will wait for a timer because you're waiting for acknowledgement to come. If you have received acknowledgement, well and good, it's amount to success. Otherwise, it is once again a failure, and you will end up in the binary exponential waiting time period, the wait TB time, and go back and do the operation again. That is the whole operation corresponding to CSMACA. Now, there may comes an occasion in which other nodes will also start sending their RTS exactly at the same time. So there must be a collision. So how to avoid that collision? Simply, there is no solution how nodes will say, because once there will be a collision, obviously the destination node would not return back CTS. If you are not receiving a CTS, how we are dealing with it? There is a timer timeout. So obviously false, k equal to k plus 1. Then you will wait for a random TB amount of time, TB second, the calculation of a TB based on the binary exponential. That means whatever be your attempt number, if it is k, You will choose a random number between 0 to 2 raised to the power k minus 1. Whatever be that random number, you will either multiply it by whatever be your transmission time or your propagation delay, any of these numbers. For that duration, you will wait, and then once again, you will start the whole operation again. So that's how you will handle the collision during handshaking. Handshaking means RTS and CTS. Then hidden station problem, we have almost resolved using CTS operation and network allocation vector. Now the point coordination function, this is the corresponding diagram corresponding to the point coordination function PCF operation. So as I mentioned, that MAC layer has two sub layers. One is point coordination mechanism, where we end up using some sort of a polling mechanism which is centralized in nature. Whereas at the distributed coordination function, we rely on CSMA CA, which we have already seen how to use it. So this is the diagram corresponding to that. But theoretically, you can just understand that the point coordination function is an optional access method that can be implemented in an infrastructure network. This is important. In an ad hoc network, you can't use. So you require an infrastructure network. It is implemented on top of DCF and is used mostly for time-sensitive transmissions. PCF has a centralized contention-free polling access method. So that's all. So here you require, it's a contention-free algorithm, polling-based algorithm. One central authority is there which will initially poll. Once the poll will be over, then that central authority would share the network allocation vector. Network allocation vector is that who is going to use it. So others will come to know that they have to wait. That's all. Here, this is the frame format. So initial 2 bytes are there for frame control. So certain control information is there, protocol inversion, type, subtype, to DS, from DS, more fragments, retry, power management, more data. This is for wired equivalent privacy, WAP, and these are certain one reserved bit. So these 2 byte, that means 8 to the 16 bits. So that's how these 16 bits being used. So then this T is this field define the duration of the transmission time that is used to set the value of network allocation vector. So when you will share, so from source to destination, when source will share the RTS, so in these 2 bytes, it will inform, through these 2 bytes, it will inform the destination about the time duration for which it wants to occupy the channel. And then the destination node will make a network allocation vector through in CTS and share it with the other exposed nodes and other hidden nodes. These are certain addresses. So why so many addresses are there? Because address 1, address 2, address 3, and address 4. So here address would point out not only the source MAC address and the destination MAC address pertaining to the host which are into communication, but we know that one basic service set would get an access to another basic service set through access point, and the access point are the part of distribution system. Access points are the part of distribution system, so we do require the MAC address of the access point as well, that from which access point to another access point, because then only your distribution system would be able to distribute and deliver it to a particular destination access point, and from that access point, destination access point, then further to the destination address. So that's why we require 4 addresses, 2 for host and 2 for the access point MAC addresses. Then this is the sequence control. So this field, often called the ASCII field, defines a 16-bit value. The first 4 bits define the fragment number The last 12 bit define the sequence number, which is same in all the fragments. So it may be possible that whatever be the frame body, so there is a whole lot of data which you have to communicate to the another node. So in that situation, you will fragment the data first. And why it is necessary to fragment? Because here error rate is more. So instead of retransmitting the whole data, if there would be an error, we have to retransmit a small part or the small fragment of the data. So for that purpose, we will approach this through fragmentation. So for that purpose, this SC would define the 16-bit. Out of that, 4-bit will be common for all the fragment. That means in total 16 fragments are possible. 16 would be common, and another one would define the first 4 bits would define the fragment number, which will be common for all the further fragmented one. Yes, the last 12 bit define the sequence number within that fragmentation. Then this is the frame body. That means where we will insert the data, and frame check sequence is nothing but the CRC of the complete frame. So for error control, so this is the frame check sequence 4 byte. Now we will see this frame control. So version we know, so the current version is 0. You can check what is the current wireless version. I think it not be 0 now. So that will be the version, that which version of the wireless LAN we are using. So that is the version. Then the type. So here the type, there are 3 type of frames. So that defines this type. So 3 types of frames. One is the management frame. So management frames are used for the initial communication between stations and access point. So when we will interact with the access point, so these are the initial management operations, the management frames. Then there are certain control frames. So control frames are used for accessing the channel and acknowledging frames. So for accessing the channel and for acknowledging the frames, for acknowledgement purpose, we have the control frames, and then the third one is the data frames. So to define that operation, we have type. Then after type, we have subtype. So there are, so we will define those subtypes using 4 bits. So that we can see here. So this is the subtype. You have 1011, that is the RTS packet. 1110, it's a CTS packet, and 1101, that is an acknowledgement packet. These are the subtype in control frames, particularly in control frames. So these are the control frame subtypes. So then we have 2 DS and from DS. This is the access point. So 2 distribution system and from distribution system. So in another way, you can understand that DS stands for on which access systems our destination node is attached to. So that is 2 distribution system, because you are sending your frame towards distribution system. So for that purpose, so this is the emphasis, the 2DS, whether, so if it is written 0 here, that means we are not going toward distribution system. If from DS, that means we are receiving something from the distribution system. From one access point to another access point, when you will communicate, then both 2DS and 1DS will be 1. So that is the idea. So when we are about to use, in case of distribution system, either we are using it towards, when we are sending it towards the distribution system, that is away from the access point, we have to use the distribution system for sending. In that case, we are sending our packet towards distribution system. So 2DS will be 0, 1 in that situation. If we are receiving something, in that case from DS, so if it is coming from another base service set, so in that situation from DS will be 1. That is the idea. More fragment is that whatever be the frame body, this is not the last, there are many more fragment which are sharing the same common initial 4-bit. So you have to compile each and everything together and then process it. So that is there. Retry again when you will do it. Power management, these are for power management, more data. This is for security purpose, and this one is for result purpose. So more retry is when set to 1 means it's a retransmitted frame. That is not to the first one. That is power management when set to 1 means station is in power management mode. More data when set to 1 means station has more data to send. Wired equivalence privacy, and this is result. This is the format of RTS. FC, D, address 1, address 2, frame check sequence. CTS and acknowledgement, frame check, that is frame control, bits, D bit, address 1, FCS. Means not the entire address it's going to be used. Now, with respect to how we will decipher the addresses, because there are 4 address part. You can see here there are 4 address part: address 1, address 2, address 3, and address 4. Based on type and subtype, we have seen the formats, the control frames. RTS is this, CTS is this. Now, in general, when the frame contains the frame body, in that situation, 2DS and from DS will make a whole lot of difference. Then based on 2DS and from DS, we will be able to decipher address 1, address 2, address 3, and address 4 well. So 2DS and from DS, as I have mentioned, that towards distribution system or from distribution system, in that situation you can see if it is 00, that means within basic service set. So one node wants to communicate within the same basic service set. It doesn't want to use even an access point. In that situation, address 1 is the destination, address 2 is the source, address 3 is whatever be the basic service set ID, that, and address 4 is not applicable. If toward destination distribution system is 0, from distribution is 1, that means the frame is destined for a node which is a part of basic service set corresponding to which we are talking, and it is coming from outside. So it is coming from, so address 1 destination, address 2 sending access point, and address 3 is the source which has send it, whose access point is the sending access point. Then 2DS and from DS is 0 and 2DS is 1. In that situation, address 1 is the MAC address of receiving access point, and address 2 is source, address 3 is destination. If both is 1, that means address 1 and address 2 are receiving access point, sending access point, and address 3 is the destination address. So here you can see these cases. Now these are the certain specifications corresponding to the physical layer over which we will use a specific standard. If we are using 802.11a, so in .11 there are 3 technique: frequency hopping split spectrum, and the direct sequence split spectrum. And so here the band is, so it is going to use ISM band 2.4 to 4.8, 2.4 to 4.8 gigahertz. Modulation is frequency shift keying with frequency hopping split spectrum. With direct split spectrum, we are going to use the modulation PSK, phase shift keying. This is the rate. Now 802.11a, this is the next version. Here we are relying on orthogonal frequency division multiplexing. The band is in the range of 5.7 to 5.8 gigahertz. We can use any one of these modulation, PSK or quadrature amplitude modulation. 6 to 54 Mbps. B, the technique is so the technique for accessing. So that is the channel access is distributed sequence split spectrum, and 2.4 to 4.8 PSK, 5.5 to 11 Z OFTM and N OFTM. G and N, the difference is the band 2.4, here it is 5.7. Modulation is different too. and rate, as you can see, it is increasing. So that's all regarding CSMA, CA, and the wireless LAN. So these are the slides corresponding to, already we have studied these things under the topic of frequencies hopping split spectrum. Seeing these things, that's all.